Santa Claus came to your house and gave you two gifts, and he told you that the two gifts contains a soccer ball and a basketball. Without opening the box, you have no way of knowing what's inside the box. Once you open it and saw the box contains a soccer ball inside, then you will immediately know the other box contains basketball. In some ways, the basketball and the soccer ball are entangled. This is the basic of quantum entanglement. When two particles, such as a pair of protons or electrons, become entangled, they remain connected even when separated by vast distance. Let's say that two electrons are emitted by a quantum system. Because the momentum is always conserved, if one of the electrons has spin left, the other one must have spin right. If the spin of one is known, the spin of other is known instantly. If that's the case, does it mean that the particles have to send information to each other faster than the speed of light? Einstein wasn't happy about this theory because nothing can travel faster than the speed of light, and he argued that the particles must contain hidden information about their spin direction when it's created. It's just that we didn't know this information, and this is called local hidden theory. For example, if I ship one pair of gloves separately to two people, Alice and Bob, if Alice observes that the glove is left hand, Bob will immediately know that the glove in his box is right hand. The gloves already contains the information of being left glove or right glove even before we observe it. That means particles doesn't have to send information to each other because their motion is always planned. They agree to behave the opposite way when they are measured. Scientists had no way to prove whether Einstein was right, until in 1964, John Bell's famous inequality experiment could test whether entangled particles contains hidden information all alone or not. There are two spin detectors, each capable of detecting spins in three different directions. Two entangled particles are sent to both detectors and it'll detect its spin. This procedure is repeated over and over, and Bell records the percentage of time that the detector measures opposite spin. This percentage will determine whether it contains hidden information or not. If the object contains hidden information, they all have a secret plan on which way they'll spin. If proton A say, "I'm gonna spin right for all directions they measure me," proton B will say, "Okay, I'll give spin left to every direction they measure me." No matter which direction you look at, they will always have opposite spin. If you choose a random direction from detector 1 and combine with a random direction from detector 2, the percentage of getting opposite spin is 100%. And there's also a second scenario. Proton A gives spin right for the first direction, spin left for the second direction, and spin right for the third direction. Proton B gives opposite spin, spin left for the first, spin right for the second, and spin left for the third. In this scenario, if you choose a random direction from detector A and a random direction from detector B, you'll have a 5/9 chance, or 56% of time, getting opposite spin. We got 100% for the first scenario, 56% for the second scenario, so if there are hidden information, Bell should get opposite spin larger than 56% of the test. However, John's experiment measured opposite spin exactly 50% of the time, which proved that there are no hidden information. Now, how does quantum mechanics account for this? Say the proton is spinning to the left and is measuring this detector. The proton is measured in direction 1 and it will 100% be spinning left when measured. This is intuitive because the spin direction and the direction of the measurement are both horizontal. It's not the case when we look at direction 2, which forms a 120-degree angle with the horizontal axis. The detector will not always measure its left spin. The probability of measuring its left spin is sine square of angle over 2, and in this scenario, only 3/4 of the time it will measure left spin. For direction 3, it also forms a 120-degree with the horizontal axis, and also has a 3/4 chance of getting left spin. This is the key to understand this experiment. Now let's look at two entangled protons measured in these two detectors. Proton A is measured in direction 1, and it will be measured to have a right spin 100% of the time. And proton B is also measured in direction 1. It will have spin left 100%, always opposite spin of proton A. For the other two directions, proton B will always have 3/4 chance of getting left spin. Remember, the other proton is measured in direction 1, getting 100% spin right, and getting opposite spin would be 1/3 times 1 plus 1/3 times 3/4 plus 1/3 times 3/4, which will give us 1/2 of the time it will measure opposite spins. It is going to be 1/2 no matter what direction you choose, and this 50% chance proves the magic of quantum entanglement. According to quantum mechanics, the two particles can be described using one wave function, so the two particles are considered one object. So they actually don't need to send information to each other at the speed of light. Quantum entanglement is used in a lot of modern technologies, such as quantum computing and quantum cryptography, but still, there are a lot of mysteries around quantum entanglement. So if you are interested, why not go explore?